Okay? Next, system calls. So system calls provide a means for a user or application programs to call upon the services provided by the operating systems. From the previous slides, okay, so every time a user or a program needs services coming from the operating systems like program execution, communication, etc., they are just using a system call. So it's just like we are calling a function of an operating system so that we can use it. All right. So mostly accessed by programs via high-level application programming interface or API rather than direct system call use. Okay. So three most common APIs are the Win32 API for Windows, POSIX API for POSIX based systems including Unix and Linux and Mac OS, and Java API for Java Virtual Machine or JVM. Okay. Okay, so next, these are example, or this is an example of a system call. Okay, so generally written in C or C++, although some are written in assembly for optimal performance. Okay, so this figure illustrates the sequence of system calls. All right, so these are the system calls here. Okay, so this requires to copy a file. Okay, so you can use stras or strace to see more examples of a large number of system calls invoked by a single simple command. So read the man page for strace and try some simple examples. Strace mkdir, temp, strace cd temp, strace date, okay, and so on. So basically, with this one, the system call sequence to copy the contents of one file to another. So source file could be .cpp, .java, but this one is, of course, as what I've said earlier, is in C or C++. Okay, and then, of course, that would be converted or translated into a destination file, which, okay, mostly this file is basically an executable or okay, any other forms, or in this case, the source file, okay, and the destination file would be the other file, okay, or the copy of the other file. All right. Next, example of standard API. So most programmers do not use the low-level system calls directly, but instead use an API or the application programming interface. Okay, so the following sidebar shows read call available in the API or Unix-based systems. Okay. Next, system call implementation. So typically, a number is associated with each system call. Okay, the system call interface maintains a table indexed according to these numbers. And this system call interface invokes the intended system call in OS kernel and return status of the system call and any return values. Okay, so the caller needs to know nothing about how the system call is implemented. So basically, if you are a programmer, we don't care about how the system call was implemented. We simply call it and use it. That's it. Okay, so just needs to obey the API and understand the OS will do us a result call. So most details of the OS interface hidden from the programmer by the API. So managed by runtime support library. These are the set of functions built into a libraries, including with the compiler. Okay. So the use of API instead of a direct system calls provides for greater program portability between different systems. The API then makes the appropriate system calls through the system call interface using a table lookup to access a specific number of system calls, as shown here in the figure. All right. Next, system call parameter passing. So often, more information is required than simply identity of the desired system call. So the general methods used to pass parameters to the OS, the simplest is pass the parameters in registers, right? Or parameters is stored in block or table in memory and address of block passed as parameter in a register. So this approach is taken by Linux and Solaris. Okay? So also, parameters placed or pushed onto the stack by the program and popped off the stack by the operating systems. We'll be covering this, okay, in the latter chapters and discussions. So block and stack methods do not limit the number or length of parameters being passed. Okay, so this one is parameter passing via table. Okay, parameters are generally passed to system calls via registers, or less commonly by values pushed onto the stack. So large blocks of data are generally accessed indirectly through a memory address passed in a register or on the stack as shown here. Okay? Alright, so next would be types of system calls. So basically we have 6 major categories outlined on this PowerPoint presentation, and we are going to start with process control. So under process control, okay, so this process controls allows the following activities or access. So create process, terminate process, and abort, okay, load, execute, and so on. So that's one. Okay, so as what I've said, there are 6 major categories of the system calls. So first is process control. Second is file management. So it allows us to create file, delete file, close or open file, read, write, reposition, get and set file attributes. Okay, that is under file management. Second. Third, you've got device management. So under device management system calls, so the users can request device, release device, read, write, reposition, and so on. Okay. Next is information maintenance. All right. So under information maintenance, you've got get time, date, set time or date. Okay. So take note that we can do changing of time and date on our computer systems, and we're just calling the information maintenance system calls. All right. Communication system calls create, delete communication connections. Okay. So send, receive messages if message passing model the host name or process name, or from client to server and vice versa. All right. So if the applications is capable of communicating with the outside world, all right, so that means we are using this communication system calls. All right. And the last one is protection. So control access to resources, okay, authorization, get and set permissions, allow and deny user access. Okay, so basically under protection system calls, it tackles more on the authorization, okay, and authentication also. All right, so these were the 6 categories of system calls mentioned earlier: process, file, device, information, communication, and protection. Okay, and this table here summarizes, okay, it shows the comparison, okay, or similarities if there is, of Windows and Unix system calls. All right, so in Windows, when we create process, in Unix we call it fork. Okay, creating a process means fork in Unix. Exit process is also exit. Okay, waiting for single object is wait here. Okay, so these are examples of Windows and Unix system calls. All right, next, standard C library example. So take note that when we are doing our first program, okay, hello world, in C or C++, okay, so we often use this sharp include stdio. So this is what we call library or directives. All right, so standard library calls may also generate system calls as shown here. All right, so as shown in C++ or any programming language, we are using a system calls there. So C program invoking printf library call, which calls write system call. So that means printf, we want to print something on the screen. So we are calling a write system call there. All right. Okay. So next would be Arduino. So IoT is getting popularity, and basically this Arduino is single tasking. There is no operating systems on it. All right. So programs, okay, named Sketch is loaded via USB into a flash memory. So single memory space, bootloader, loads program, and then program, exit, shell reloaded. Okay. So this is how it looked like. Basically, at system startup, you have the bootloader, and then you've got a free memory there. Okay. So when you run the program, okay, so we copy the user program or the sketch on the free memory, and then that's it. Again, in Arduino, no operating systems on it. All right. All right, so next is FreeBSD. So FreeBSD is a Unix variant, just like Linux. Okay, so it is multitasking. User can log in, invoke user's choice of shell. Okay, shell is the CLI of a Unix-based systems. All right, so shell executes fork. Fork meaning we are going to create a process from the table presented earlier. Okay, so process exits when code equals 0, that means no error, or code is greater than 0, that means there's an error code. All right. Next, system services. So system programs provide OS functionality through separate applications which are not part of the kernel or the command interpreters. Okay, so system programs provide a convenient environment for program development and execution. So they can be divided into this. All right. So most users' view of the operating system or operation of the system is defined by the system programs, not the actual system calls. Okay. Next, system services continuation. We've got file management. So this basically detailed, okay, this file manipulation, status information, and so on the next slide here. So they are also known as system utilities or system applications. So most system also ship with useful applications such as calculators, all right, or simple editors like Notepad. So some debate arises to a border between system and non-system applications, all right. So system programs may be divided into these categories. Okay, so you've got file management programs to create, delete, copy, rename, print, list, and generally manipulate file and directories. All right. You also have the status information, utilities to check on the date, time, number of users, processes running, like what I've shown earlier, using the task manager, data logging, etc. So system registers are used to store and recall configuration information for particular applications. All right. So next is file modification. So example, text editors and other tools which can change file content. So we call it file modification. All right. Programming language support. Example, compilers, linkers, debuggers, profilers, assemblers. So library, archive or archive management. Okay. Interpreters for common languages and support from it. Okay. So next is communications. Programs for providing connectivity between processes, or when we say process, these are program and execution or running program, and the users. So including mail, web browsers, remote logins, file transfers, okay, and remote command execution. So that's under communications. All right. Next, background services. So system daemons are commonly started when the system is booted and run for as long as the system is running. So handling necessary services. Examples include network daemons, print servers, process schedulers, and system error monitoring services. All right. And the last one is application programs. So don't pertain to system. Okay. So when say application programs, these are run by the users, not typically considered part of the operating systems. Okay. All right. So next is linkers and loaders. All right. So source code compiled into an object file is designed to be loaded into the physical or any physical memory location. So relocatable object file. It's just like when we created our first program in C++. Okay, so basically what we see on the screen is our source code. All right, and that source code is usually in .cpp format. Okay, so this source code, when we compile it, well, that generates an object file. Okay, so linker combines this into a single binary executable file, also brings in libraries. So program resides on a secondary storage as binary executable, must be brought into the memory by a loader to be executed. Okay, so relocation assigns final address to a program parts and adjusts code and data in program to match those addresses. So modern general purpose systems don't link libraries into executables. Rather, dynamically linked libraries, or DLL, so that is what we use in Windows, are loaded as needed, shared by all those that use the same version of that same library. Okay, so object executable files have standard formats, so operating system knows how to load and start them. Okay, so if you will observe in C++, no, during our early days in programming, okay, so once we created a program, let's say .cpp, okay, so we usually compile it. Okay, so with a successful compiling, okay, meaning no errors, so that generates an object file. Okay, that object file, when we run that program, okay, and that object file is executed, so we can see an output on the screen. All right, so that's what we do during our early days in programming. So that uses linkers and loaders. Okay, so compilers are used for high-level language programming, and in low-level, instead of compilers, we use assembler. Okay, so compiler, high-level programming, assemblers, low-level programming. Okay, so what is the role of the linker and the loader? So for example, this is what I'm talking earlier. Okay, so for example, you have the source program, main.c or main.cpp. Okay, so when we compiled it, it creates an object file. Okay, so next is when we load it. Okay, so the linker with other object files associated with that will generate an executable file. Okay, so that's the linker there. So compiler, linker. So compiler from source to object file, from object file to executable file, linker. And if there are other object files there, so that would be linked up also. Okay, and then executable file to be loaded onto the RAM for execution, and calling other dynamically linked libraries, or DLL, so that is where loader comes in. Okay, so basically we don't care about this during our early days in programming. All right, so what we want to see there is just our code or our program is successfully running. All right.